Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, today I'm going to show you how food scientists use acid-base titration and indicator to determine acidity of fruit juice. For this example, we will be analyzing the acidity of orange juice sample by using a phenolphthalein as our indicator. In real food labs, controlling acidity is extremely important because it affects flavors, preservation and food safety.
Next, analytical objective. We need to determine the percent acidity in weight per volume of citric acid in an orange juice sample using acid-base titration. And it is not just do a titration, but it's to use phenolphthalein as the indicator to determine the percent acidity in orange juice. Have you guys ever wondered why we use phenolphthalein as the indicator? First of all, you guys need to remember that not all indicators are the same. Imagine they are like specialized detectives that only work in specific zones. So, phenolphthalein is a detective that works in the basic zone. Then, if we go further, we choose phenolphthalein because it has perfect pH match for this case. Phenolphthalein will change color between pH 8.2 to 10.0. As you guys know, the main acid in orange juice is citric acid, which is a weak acid, and we want to titrate it with a strong base like sodium hydroxide. When we are titrating a weak acid with a strong base, the solution will be slightly basic at the equivalent points, which pH value is bigger than 7. It is because when we are titrating a weak acid with a strong base, the product at the end point is the conjugate base of the weak acid, which then hydrolyzes to create a basic solution. Other than that, phenolphthalein also has a clear endpoint, which is from colorless to faint pink. Phenolphthalein also fast, consistent, and easy to detect. In conclusion, phenolphthalein is a perfect mesh for this case because its color change zone is a perfect mesh for the slightly basic endpoint of a weak acid strong base titration. As you guys can see below, this is the data for our orange juice acidity calculation. So, let's read it together. For the sample, we have 10 ml of orange juice, and this is the amount we are checking. Next, the titrant. The titrant we use is sodium hydroxide. It has 0.1 m of molarity, and this is our standard base solution. Next, the average sodium hydroxide volume used is 12.3 ml. This is the volume when phenolphthalein turned pink, and this is our most important data point. Last but not least, the acid that we are calculating is citric acid. For a complete neutralization of citric acid, all the 3 acidic protons on the citric acid molecule will be neutralized. For the required calculation, step 1, you need to convert sodium hydroxide volume to liters. You can get the volume from the data given. Step 2, you need to calculate the moles of the sodium hydroxide. Step 3, you need to calculate the mole of the citric acid. We can find the mole by using the 1:3 ratio from the balance equation. Step 4, we need to calculate the grams of citric acid in our orange juice sample. Lastly, step 5, we need to calculate the percentage of acidity in weight per volume.
Based on the data we have, we will do the work example to find the final answer, the percent acidity of the sample. Step 1. Convert now volume to liters as molarity is in moles per liter. So value of now 12.3 ml multiplied by 1 liter over 1000 ml, and we got the answer 0.01230 liter. Step 2. Calculate moles of now. The moles of now are calculated using the molarity and the volume used in the titration, n equal to mv. So the molarity of now we got 0.1 mole per liter, so we just need to substitute into the equation. Moles now equal to 0.1 mole per liter multiply with 0.0123 liter, and we got the answer 0.00123 mole. Step 3. Calculate moles of citric acid. Using the 1:3 stoichiometric ratio from the balance equation, 1 mole citric acid per 3 mole of now. So mole of citric acid is equal to 0.00123 mole divided by 3, so we got the answer 0.00041 mole. Step 4. We need to convert moles of citric acid to grams. So the mass of citric acid is calculated using its molar mass. So gram citric acid is equal to 0.0004 mole. Multiply with 192.12 gram per mole, and the answer is 0.0788 gram. Step 5. Calculate percent acidity. Percent acidity weight over volume is the mass of citric acid in gram divided by the volume of the original sample. So for the sample volume is 10 ml, so we just need to substitute. So we got the percent acidity is equal to 0.0788 gram divided by 10 ml multiply with 100%, so we got the final answer 0.788%. Concept of citric acid titration. Citric acid is a triprotic acid, meaning it possesses 3 acidic hydrogen atoms that can be donated in aqueous solutions. For the stoichiometric ratio, because there are 3 acidic protons to neutralize, the complete reaction requires 3 moles of a strong monoprotic base NaOH for every 1 mole of citric acid. This established the crucial 1:3 molar ratio used in the calculation. So for the balance equation, we got 1 mole of citric acid plus 3 mole sodium hydroxide. We got the product 1 mole sodium citrate plus 3 mole of hot water. Equivalent point versus endpoint. Equivalent point is the theoretical point where the moles of NaOH added are chemically equal to the moles of the acidic proton H+ present in the citric acid based on the 1:3 ratio. So for the endpoint, this is when the benefited indicator changes color from colorless to light pink at a pH that is very close to the equivalent point of this specific reaction, signaling the practical completion of the neutralization. This pH is slightly basic because the product sodium citrate is a salt of a weak acid and a strong base.